Today, we're diving into this really fascinating corner of math and computer science. We're going to tackle a question you might not have even thought to ask. What if you could translate one type of logic into another? And what if doing that could turn some abstract idea into a concrete, usable recipe? Let's get into it. So first things first, when you think about logic, you probably imagine just one way of doing things, a single system of true or false. But what if I told you that's not the whole story? Not even close. What if there are different, totally valid ways of reasoning? This question right here is what sets the stage for everything else. To really get this, we got to look at two main schools of thought. On one side, you've got classical logic. It's totally fine with a proof that says something like, hey, I can prove this thing must exist, even if I can't actually show it to you. That's called a nonconstructive proof. But then, on the other side, you have intuitionistic logic, and it is way stricter. It says, nope, if you want to prove something exists, you better show me a concrete example or give me a step-by-step method to build it. So you have these two totally different worlds, right? Almost two different languages for reason. For a long, long time, they seemed pretty incompatible. But what if you could build a bridge between them? Well, that's where our hero comes in. This amazing technique that lets us translate ideas from that classical world over to the intuitionistic one. It's called the negative translation, and as our source material puts it, it's a powerful way to translate classical logic into intuitionistic logic while making sure that the core idea of provability is preserved. This isn't just some clever little party trick. It's a really fundamental tool for understanding how these two logical systems relate to each other. And you don't have to take my word for it. The experts call it a quite natural translation, which is both simple and powerful. I mean, isn't that the holy grail in math and science? An idea that's elegant, it's straightforward, but it has these incredibly profound consequences. So how does this magic trick actually work? Well, you start with a classical proof. Then you run it through this special double negation filter. What it does is it rephrases key statements by adding "it is not the case that not," which, sounds a little clunky, but it subtly changes the entire logical structure. And the output? A brand new proof that is now perfectly acceptable in that much stricter world of intuitionistic logic. Of course, an idea this huge didn't just pop out of nowhere. It wasn't one person. It was actually built over decades by some of the greatest minds in logic and mathematics. The whole journey really kicks off in the 1920s with Kolmogorov laying down the groundwork. Then you see Glivenko applying the idea to propositional logic. After that, the legendary Kurt Gödel and Gerhard Gentzen come along in 1933 and refine it even more. And the idea just kept evolving, with people like Kuroda developing their own unique spins on it as late as 1951. Each person built on the last, making this incredible logical bridge stronger and stronger. Okay, so this is all really fascinating stuff for logicians, but why should you and I care? Well, this is where the story takes a really practical and very modern turn. This isn't just about abstract proofs anymore. It's about computation. The real power of this whole thing is captured perfectly by our source material. It allows for extracting constructive computational content from seemingly non-constructive classical proofs. Just let that sink in for a second. We are pulling real, usable computational information out of what seemed like purely abstract ideas. And here's what that actually means in plain English. Remember that classical proof that just said, I know a solution exists, trust me? Well, by translating it, we force it to become an intuitionistic proof. And what does an intuitionistic proof always demand? A construction, a method. So this translation literally turns an abstract statement of, I know it exists, into a concrete, here is the recipe to find it. The implication here is just staggering. This technique means we can go back to old math proofs, I'm talking stuff written decades, even centuries ago, and use this translation to discover hidden algorithms, hidden computer programs that were just lying dormant inside them this whole time. It's like we're doing computational archaeology. And this is not just a history lesson, not at all. The story of the negative translation is still being written. Researchers today are pushing these exact same ideas into totally new territories. So now we're seeing these translation techniques being explored in all sorts of advanced systems. They're being used in things called substructural logics, which are super important for modeling resources in computer science, and in other more exotic systems like affine logic and Lukasiewicz logic. They can even be used to pull out specific numerical data from classical proofs in analysis. The applications just keep growing. So, what's the secret ingredient that makes it all work? Well, a lot of the time, it relies on this logical principle called the contraction rule. Basically, it's the idea that you can reuse a fact as many times as you want in a proof. But what's really exciting is that current research is figuring out how to make these translations work even in new logical systems where that rule is restricted. This is seriously the cutting edge of what logic can do. So let's just end on this thought. We started with what looked like two completely incompatible ways of thinking. One was abstract, the other was concrete. And we found a bridge, a translator, that didn't just connect them, but actually unlocked incredible practical value. It really makes you wonder. If something as fundamental as logic can be translated, revealing hidden recipes inside of old ideas, what other foundational concepts out there are just waiting for the right translator to come along and reveal their secrets?